Okay, the pendulum is, it's a child on a swing. That's a pendulum motion. Anytime you have a length of string, a rope or whatever, attach it to a fixed point, and then you have something swinging back and forth. That's called the pendulum. Let's start off with a demo. This is a demonstration of the simple pendulum. The simple pendulum is this kind of motion where you have a mass on the end of an, ideally, an inextensible string, a string that can't be stretched. And it oscillates with a particular period, and the period is defined as the time for one complete oscillation. So here it looks like the period is roughly 1 second, boom, boom, a little longer than a second, boom, etc., etc. So we want to think about today how that period depends on the various parameters of the problem. We'll work out in class, or have already worked out in class, the dependence of the period. The period is denoted by the capital letter T. It goes like 2 pi the square root of L, which is the length of the pendulum, this length from the center of mass up to the point where it's attached, divided by g, the acceleration of gravity. And notice that this period does not depend on two things you might have thought that it could depend on: the amplitude of the motion, which is the angle from the vertical. This is the equilibrium position of the pendulum. If I put the ruler roughly where that vertical line is, and then I bring the pendulum out, the angle that is made between the green string here and the ruler is maybe about 10 or 15 degrees in this particular case. That is the amplitude. So if I release it from rest at that angle of, say, 15 degrees, then it will come down through the equilibrium position, go 15 degrees onto the other side, and then back and forth like that. So that's the amplitude. Let's first investigate the dependence of the period, the time for one complete oscillation, on the amplitude. At this amplitude, it may be 15 degrees, it's boom, 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 2, 3, boom, 2, 3, about that. And let's try a smaller amplitude. Boom, 2, 3, boom, 2, 3, boom, 2, 3, boom, 2, about the same. At least very difficult to detect any difference. Let's do this intermediate amplitude. Boom, 2, 3, boom, 2, 3, boom, 2, 3, etc. Galileo, when he was in church back in Italy, there was a wind blowing through one of the windows, and there was a chandelier that was oscillating as a simple pendulum. And he, using his pulse as a stopwatch, timed the oscillations of that chandelier and determined to his satisfaction that the period does not depend on the amplitude. And in fact, the period does depend on amplitude. When the amplitude gets large, like this amplitude, the period is a little bit longer than it is for simple harmonic motion. But that calculation is a very difficult one to show the dependence of the period on the amplitude. What we'll do in class is to simply consider very small amplitudes, maybe about 10 degrees or smaller. And for small amplitudes, the period does not depend on the amplitude at all. It depends only on the length of the pendulum and the gravitational acceleration. The next interesting thing to look at is the dependence of the period on the mass. So let me do a small angle so this equation will be valid. Boom, 3, 1, 2, 3, 1, 2, 3. Let's change the mass. This is 200 grams. And this is 100 grams. Use a small amplitude again. 1, 2, 3, 1, 2, 3, 1, 2, 3. No change. We can even go to an even smaller mass, and you see again 1, 1, 2, 3, 1, 2, 3, 1, 2. So no dependence on the mass. You can see that in this equation. So now let's look at the dependence of the period on the length. Clearly, this equation says that if you increase the length, given that the period depends on the square root of the length, then you will increase the period. So let's remind ourselves what the period is here with this particular length. Boom, 2, 3, boom, 2, 3, just as we had before. And let's increase the length then. Boom, 2, 3, boom, 2, 3, boom, 2, 3. So the period is now longer. The time for one complete oscillation is longer. It looks to be 2 or 3 seconds instead of roughly about 1 second. And that's consistent with the equation here. You could do more careful calculations, but that shows you the basic dependence of the period on the length, the independence of the period on the amplitude. And then the other thing that the period depends upon, of course, is gravitational acceleration. The Earth's gravity is 9.8 meters per second squared. If you were to take this pendulum and set it up exactly like this on the moon, where gravity is much less than it is on the Earth, you have a smaller gravitational acceleration. And given that that's in the denominator, you'd have a longer period. So it would take a longer time to make an oscillation with the same length that it would on Earth. Okay, we're going to derive the period of a simple pendulum for small amplitude oscillations. For small amplitude oscillations, like we talked about in the demo video, those are ones where the string never moves very much away from the vertical position. So this angle here is going to be small. If it's small, then the string is essentially vertical, and gravity and tension are essentially opposite each other. And so for small angles, that's true, at least approximately so. And then the forces that comes from the forces in the y direction. But for forces in the x direction, we're going to need some kind of restoring force. And the sum of forces on this mass in the x direction is going to be mass times acceleration in that direction. So this is the x component of the tension. Here's the angle theta. And you can see that this x component of the tension, first of all, it's pointing in the negative x direction, so it's going to be negative. And second of all, it's going to have to involve the sine of the angle theta. Why is that? Because this side is opposite to this angle. So we'll get a minus t sine theta for the x component of the tension. And that's the only force in the x direction, because gravity doesn't exert any force in the x direction. Equals mass times acceleration in the x direction. But we can do a little bit of geometry and notice that sine of theta is x over L. So if we look at this big triangle here, I've got sine of theta is the side opposite over the hypotenuse. That's x over L. And so I'm going to substitute this relationship into here. So now I've got x over L instead of sine theta. I'm going to substitute this t into here. T is mg. And now some approximations and miracles start to happen. The mass cancels out. And I'm going to then apply this equation at t equals 0. And as you remember, at time t equals 0, it's at its maximum displacement and its maximum acceleration. Both reach their maxima. So x is a, acceleration is minus a omega squared, because x is positive and acceleration is going to be negative. So the acceleration is in this direction, the minus x direction. That's why you need that minus sign. And the masses cancel, the negative signs cancel, and we can solve for omega. The a's actually cancel. And so we're left with omega squared equals g over L. And I can find omega by taking the square root of g of that g over L. So that gives me the angular frequency. And that guy, it's interesting, instead of having k over m for the spring oscillator, we get the square root of k over m. We get the square root of g over L. So it's always going to be a square root of something over something else. And then we can find the period as 2 pi over omega, like we talked about before. That'll be 2 pi that comes along for the ride, times 1 over omega. Well, that's just the square root of L over G. And this is the relationship that we talked about in that demo video. So I'm not going to actually require you to know that derivation in detail, but I wanted you to be able to see it, to see where it comes from. It's similar to the derivation for the mass spring system that I have asked you to learn. State the angular, but what I am asking you to do is to be able to state the result of that derivation. State the angular frequency and the period of a simple pendulum for small amplitude oscillations. Well, this is what we found. Square root of g over L for the angular frequency, and then for the period is 2 pi squared of L over G. If you just remember this, and you already know that, then you can find this. I would just memorize as few equations as possible. In the video, we talked about the amplitude being measured as an angle, 15 degrees or whatever. You can also think about the amplitude being a horizontal displacement, the x value from the equilibrium position. So either way works. You can say that the amplitude of this motion is 4 centimeters, for example, if you move 4 centimeters to the right of the equilibrium position. Or you can say it's 15 degrees or whatever. There's 2 different ways of thinking about the amplitude of a simple pendulum. All right, under which one of the following conditions does the motion of a simple pendulum approximate simple harmonic motion? When the pendulum swings rapidly, it's actually when it swings through a small angle. We made some approximations in that derivation. We said that tension is equal to mg, but that's only valid if it's not moving very much out of that vertical line. And so it's this one that really matters. Determine the length of a simple pendulum of period 1 second. This is so powerful because you can use it to figure out the period of a grandfather clock or anything like that. I just think it's a great result. We know that t is 2 pi squared of L over G. We're trying to find the length of a period of a pendulum that has a period of 1 second. And why would that be useful? Well, you can use it for a clock. So it'll make 1 complete period every second. So it'll swing from here over to there and then back to here again in 1 second. As long as you make sure that you're in small angle oscillations, maybe less than about 10 degrees, for which the approximation is valid. Well, to solve for L, we're going to do like we did in the case with the mass spring system, square both sides of the equation, then multiply both sides by g, divide by 4 pi squared, plug the numbers in, and you get 0.248 meters. So that's about 25 centimeters, So meters like that. There's 50 centimeters, 25 centimeters, something like that. So that's pretty short. Simple pendulum consists of a ball of mass m suspended from the ceiling using string of length L. The ball is displaced from its equilibrium position by a small angle theta and released. So I actually drew this for a fairly large angle, but you have to imagine it being a smaller angle. Which one of the following statements concerning this situation is correct? If the mass were increased, the period of the pendulum would increase. Well, the period doesn't depend on the mass. We showed that in the demo video. So changing the mass is not going to change the period. That's one of the cool things about it. The frequency of the pendulum, it does, the period of the mass spring system, if you have a mass on the end of a spring, that does depend on the mass. The frequency of the pendulum does not depend on the acceleration due to gravity. Well, that's not true either, because it does depend on the acceleration of gravity. There it is. If you take it to the moon or to Mars, you're going to get a different period. In fact, one of the slickest ways for you to measure the local acceleration of gravity would be to take a pendulum to the moon, measure its period, measure its length, and then solve for the gravitational acceleration. I think I've assigned or will assign a problem or two like that. If the length of the pendulum were increased, the angular frequency of the pendulum would decrease. Not true. If you increase the length, since that length is in the numerator, then you're going to increase the period, not decrease it. The period of the pendulum does not depend on the length of the pendulum. That's also not true. It does depend on the length. There's the L right there. The angular frequency would double if the angle theta were doubled. That's also not true. The angle theta is the amplitude, and this angular frequency doesn't depend on the amplitude, so that's not true. So let's see if we've just made a mistake and not seen the correct answer. Mass were increased, yeah, the frequency does not depend on the acceleration due to gravity. That's not true. The period depends on the acceleration due to gravity, so does the frequency. The length of the pendulum were increased, the angular frequency, aha! It's this one that's actually correct. They're talking not about period here, but angular frequency. So on this one, we need to look at this equation and say what happens if I increase the length of the pendulum. Well, here's the length of the pendulum. I want to increase this guy, but it's in the denominator. So when you increase the denominator, you decrease the result. So this will decrease. The angular frequency will decrease. Okay? A fun little demo, I think anyway. This is a pendulum array demonstration. What I have is a series of pendula going from those that have a short string attached to a short string, or a pair of strings actually, to those that have longer strings. So the length of the pendulum is the distance between where it's attached to something firm down to the middle of the pendulum bob, so-called. That length appears in this equation in the numerator. So as I increase the length of the pendulum, I increase the period. And the period is the time it takes for one complete oscillation. If you increase the length, you increase the period, so the time for one complete oscillation will increase as I move from short to long. And the frequency of the pendulum goes like 1 over the period. So the frequency goes from high frequency, where it's oscillating fast, to a low frequency, a very slow oscillation. So what I'm going to do is to push all these pendula forward toward you and then release them from rest and see what happens. And so what you should be looking for is to see this one oscillating faster, it gets going faster, and that one slower as it moves along. But they create some pretty cool patterns. See waves propagating up this way now. And then they all get back into sync again, only to start another round of these transitions. And those are this is an array of pendula.